Hello everyone, welcome to the world of data structures. Our today's topic is AVL tree or height balance tree. Hi, this is your instructor Janice Shah. So let's begin with today's outline. Students, in today's lecture, first we will talk about that AVL tree or height balance tree. Then we'll see that how to calculate the balancing factor and what we exactly mean by balancing factor. Then we'll talk about the different types of examples to find out balancing factor because it is very important topic. Okay, so let's start with AVL tree. The first is AVL tree or height balance tree. So due to various type of operations performed on the binary tree, the tree can lead to an unbalanced tree. Students, if we have seen that we are performing insertion and deletion operations on binary search tree. In our previous sessions, you have already learned about that how can we do insertion and deletion operation on binary search tree. Now, if somehow if we are going to insert on the left side, like we have root node 10, okay, and if you are inserting 3, then 2, then 1, so most probably the all after inserting these all 4 values, your trees goes like this: 10, then 3, 2, and 1. Okay, so it just becomes a left sided tree. Okay, so what happens over here, your balancing between heights of left subtree and right subtree is not properly. Okay, so in such type of cases it might be possible that you have to traverse more using your traversal algorithms, and it is very much difficult to complete your traversal operations efficiently. That's why it's a concept of AVL tree over here. Okay, so what we need to do is, if your tree is unbalanced, then you need to make it balanced tree. Okay, so the question is, sir, how we can say that my tree is unbalanced? Okay, so students, the tree is unbalanced when the height of the left subtree is much more than height of the right subtree, or vice versa. That means if the height of the left subtree is 3 and the height of the right subtree is 5 or 7, that means it's a vast difference between height of left and right subtree. Okay, so that tree is known as unbalanced tree. Okay, so let's move further. The next is before insertion. See, here I am just showing you one example that in binary search tree, this is our main question, or this is our main figure of a tree where we have 79, 32, 10, 50, 90, then 85 and 95. Okay, so we have our binary search tree over here. Now, if I want to insert, like in this is my left subtree, students, this is my left subtree and this is my right subtree. Okay, so if you can see that here in left subtree, students, we have 32, 10 and 50. On the right subtree, students, we have 90, 85 and 95. Okay, so what is the height of the left subtree? What is the height of the left subtree? If you want to calculate the height of the left subtree, okay, then just go from the bottom level of left subtree. That is 10 and 50, that is 1, and 32, that is 2. So this is 1 and 2. We can go like this, 1 and 2. Okay, so that is the height of the left subtree. So for root node 79, again I am repeating this sentence, that for root node 79, students, the height of the left subtree is 2. Now, if I am talking about the right subtree height, okay, you can say the right subtree height is also 2. Okay, so here it is that for root node 79, students, the height of the left subtree and right subtree is 2. That means now here your tree is in a balancing situation. So such type of tree is known as balanced tree. Okay, now let me show something. The next we have after insertion 46, 40 and 45. Suppose this is a tree, or this is my answer after inserting consecutively 46, 40 and 5 in our previous example. Okay, so what happens after inserting such type of things, students? Now we have tree like this. This is our new left subtree which contains 32, 10, 50, 5, 46 and 40. Fine. So what happens over here, students, that now my height of the left subtree is increases. Okay, since how many levels are there total for the left subtree? How many levels are there? See, 32 at one level, 10 and 50 at another level, number 2. Now 5 and 46 at number 3, and 40 is also a next level. So here we have 4 levels. That means the height of the left subtree is, students, 4. See, 32 1, then we have 10 and 50, then 5, then 40. Okay, so here the height of the left subtree is 4. Okay, so here the height of the left subtree is 4. Now let me talk about the right subtree. See, I did not insert any element of the right subtree. Okay, so my right subtree is as it is. But if I am talking about the height of the right subtree, then how to find it out? See, for root node 79, the right subtree height is 90 is at one level and 95 and 85 is at another level. Fine. So we can easily say that the right subtree height is 2. So what happens over here, students? The height of the left subtree is 4 and the height of the right subtree is 2. So it's a huge difference between both of them. So such type of tree is known as unbalanced tree. Okay, so what is your role over here? What is the job of you? You just need to balance your tree, binary search tree, so that the traversal operation can be easily performed. Okay, so next we have the AVL tree. So AVL tree, A, V and L, all three names are the name from the scientists who defined this method. Okay, so it's a AVL tree which is also known as height balance tree, just because here we need to balance the height of a left subtree and right subtree. Okay, so AVL tree is known as a height balance tree which satisfy mostly 2 conditions. Okay, condition number 1, that the height of the left subtree and the height of the right subtree. Okay, so the difference between both of them, it should not be greater than 1. Again, I am repeating the sentence, that, students, the height of the left subtree and the height of the right subtree for a particular node, students, the difference of the LST stands for left subtree and RST stands for right subtree. So for a particular node, students, the difference of height between left subtree and right subtree should not be greater than 1. And the next condition is subtree of a node, the left and right subtree are also AVL tree. Okay, so it's not like that only root node, for considering a root node, the height should be equal. For root node subtree or root node child node, height must be equal, or the difference between the LST and RST should not be greater than 1. Fine. So now the question is, sir, how can we find out the difference between both of them? Okay, so let's see. Here we have the next terminology, that is balancing factor. Okay, so what we have, we always need to find out the balancing factor for each and every node of a tree. If your tree contains 7 nodes, then first your job is to find out the balancing factor for each and every node, and it is very much easy to find it out. Let's see. The formula for the balancing factor is the height of the LST minus height of RST. LST RST means height of the left subtree minus height of the right subtree. Okay, so here it is, balancing factor. So students, if your balancing factor, here I am just dividing balancing factor into 3 different parts. Okay, so how can you judge whether a tree is balanced or not? And if your tree is unbalanced, then what operations you should be performed? It is shown over here. So please concentrate over very much carefully, that first we have the balancing factor, and the first type of balancing factor is balancing factor is equal to 0. Okay, I am just taking an alias like b dot f dot bf is equal to 0. That means if your balancing factor is equal to 0, that means your tree is balanced tree. Okay, now what is our job? Our job is just to balance our tree. Now if tree is balanced, then you should not perform any action. Do not worry about to perform any action on that tree. Fine. Now the next we have, students, next we have with us, that is balancing factor is equal to plus or minus 1. Okay, see, the AVL tree definition contains a rule that the height difference should not be greater than 1. That means if your balancing factor is minus 1 or plus 1, then it also known as tree is balanced tree, and you do not worry about any actions to be performed on that tree. Okay, so either your tree has balancing factor 0, 1 or minus 1. Either your tree has balancing factor 0, 1 or minus 1. You should not need to take any action on that tree because your tree is balanced tree. Fine. Now the next, the number 3 is, if my balancing factor is plus 2 or minus 2. Now here the rules are violating. Okay, so here the rules are violated by our system that is known as the balancing factor is plus or minus 2. That means the difference between LST and RST now is greater than 1. Then what to do? In such situation, students, your tree is unbalanced and you just need to perform a particular actions to make your tree balanced tree. Here trees are also known as the right heavy and left heavy tree. So at that time you just need to give some rotations over there. Now what are you talking about the rotation, left heavy, right heavy? We are not understand right now. So do not worry. I'm just giving you brief about the left and right heavy very soon. Okay. So here you just need to remember that if a balancing factor plus or minus 2, that means your tree is unbalanced and you have to take some actions on that tree. Okay. Now next, balancing factor. The formula is balancing factor is equal to height of the left subtree minus height of right subtree. Okay. So here the first is balancing factor is equal to 0. That means, students, tree is balanced. Now balancing factor is plus 1. Always remember this. When your balancing factor is plus 1, then your tree is known as left heavy tree, but it is balanced. It is balanced. Okay. Now if your balancing factor is minus 1, then your tree is known as right heavy tree, but still it is balanced tree. Okay. Next is balancing factor is equal to plus 2. Students, see, whenever a balancing factor is plus 1, plus 2, plus 3, plus 4 with a positive sign, that means your tree is left heavy. Remember this. Whenever your balancing factor is plus 2, plus 3, plus 4, plus 1, whatever, any positive sign, then it is a left heavy tree. And if a balancing factor is minus 1, minus 2, minus 3, minus 4, that means it's a right heavy. Okay. But for plus 1 and minus 1, tree is balanced because the definition says that difference should not be greater than 1. Okay. But what about the rest of the part? So when the balancing factor is plus 2 or minus 2, now when the balancing factor is plus 2, then it is known as a left heavy unbalanced tree, and it is minus 2, then it is known as right heavy unbalanced tree. Okay, so for plus 2 we have left heavy unbalanced, for minus 2 we have right heavy unbalanced. But now the question is, sir, how can we calculate the balancing factor of a tree? So let's start with the examples. Okay, so first check whether a tree is balanced or not. See, before performing any operation on AVL tree, you have to find out balancing factors of a node. Okay, if your balancing factor is greater than plus 2, greater than or equal to plus 2, or less than or equal to minus 2, then your tree is unbalanced and you need to perform some action over there. Okay, so let's understand that how can we calculate the balancing factor for a nodes. See, let me start balancing factor. Okay, let me start with the root node 10, sorry, leaf node 10. So students, now tell me, is there any left subtree exist for root node 10? Yes or no? No. is there any right subtree exist for leaf node 10? No. That means, students, here leaf node 10 does not contain any left subtree or any right subtree. That means the height of the left subtree for node 10 is 0. Height of the right subtree for node 10 is 0. So 0 minus 0 becomes 0. That's why here the balancing factor for leaf node 10 is 0. Now let's move further. Next, for 32. Students, tell me, what is the height of LST for node 32? See, just calculate the height one step below. Okay, so here the 32, child is 10. So it's only one level hierarchy for left subtree node 32. That's why the left subtree height is 1. For node 32, the height of the left subtree is 1 and the height of the right subtree is 0. That's why the formula is given over there. For the balancing factor, if you want to find out the balancing factor for node 32, then it must be height of LST, that is 1, height of RST, that is 0. So 1 minus 0 becomes plus 1. Okay, now let's move for the 85. See, again 85. For node 85 is a leaf node. 85 does not contain any left subtree or right subtree. That's why the 85's height of left subtree must be 0. Right subtree height is 0. 0 minus 0, the total becomes 0. So the balancing factor for node 85 is 0. Now for node 95. Again 95 is a leaf node. Balancing factor is 0. Okay, now let me talk about the next example, that is 90. Okay, so students, 90 for node 90. Now tell me what is the height of LST for node 90. So students, you can easily say that from the figure that for node 90, sir, the left subtree height is 1. Left subtree height is 1 because it's only one level below of 90. Fine. Now the right subtree height is also 1. Okay, so here 1 minus 1 becomes 0. So the balancing factor for node 90 is 0. Fine. Now our last root node. So now tell me, students, what is the height of LST for the root node? So if you can say that the left subtree height for node 79 is 2. For left subtree height, okay, for left subtree height of node 79 is 2 because there are two levels, 32 and 10. One level at 32, one level at 10. Now tell me, what is the height of right subtree? First for the 90 level and then 85 and 95. So it's again 2. One level is for 90, another level is for 85 and 95. So it's again 2. So here the balancing factor for 79 is 2 minus 2, which is becomes 0. Students, never do a mistake to calculate number of nodes in left subtree. Here we need to count levels. Okay, count levels for height. Please, many of the students are making mistakes like they are just calculating number of nodes. That's here in LST we have number of node 2. In RST we have number of node 3. So 2 minus 3 becomes minus 1. It's totally wrong. It's totally wrong because here we just need to count the number of levels in left subtree or right subtree. Fine. So here the balancing factor of the 79 becomes 2 minus 2 is equal to 0. Then that's the next example. Okay. So here the 2 minus 2 0. That's why this tree is a balanced tree because the root node contains balancing factor 0. That's why this tree is balanced tree. Fine. Now let me take another example. This is the example we have. Okay. Now let's start finding out calculate the balancing factor of these nodes. Okay. So we have 15, 45, 85 and 95 with us. These all four nodes are leaf nodes. Students, leaf node does not contain any child. That means there is no LST and RST for these nodes. So height of the LST and RST becomes 0. So 0 becomes minus 0 becomes 0 again. So for 15 BF is 0. For 45 balancing factor is 0. 85 balancing factor is 0. And 95 the balancing factor is 0. Now if you can see, students, after each and every calculation, I am just writing balancing factor at the top of the node. You have to write like this for in your notebook. Okay, you have to mention a balancing factor over the node. Okay, whether it is minus 2, plus 2, plus 1, minus 1, 3, 4, whatever. Fine. Okay, so here I am just defining balancing factor for each and every leaf nodes. Now let's start with the node 40. Now for node the 40, students, if you can say the left subtree height for node 40, the left subtree height is 0, and the right subtree we have one level, that's why 1. So 0 minus 1 becomes minus 1. So here it is, this is 40 is minus 1. Okay, so the balancing factor of 40 is minus 1. Okay, now the next we have 30. So students, tell me for node 30, what is the balancing factor? See, the height of the left subtree of 30 node is 1, because only one level is there. Okay, in left subtree of 30 we have only one level, and on the right subtree of 30 we have two levels. That's why 1 minus 2 becomes minus 1. The balancing factor for node 30 is minus 1. Now let me talk about the 90. See, 90 contains one child or one level at the left subtree, one level at the right subtree. That's why balancing factor of 90 becomes 0. Now tell me what is the balancing factor for node 70? Okay, students, let me calculate first. For node 70, see, if this is node 70, okay, this is node 70, okay, then left subtree we have 30 at a one level, and next level we have 15 and 40, okay, and the next level we have 45. So there are three levels for left subtree heights. That's why the height of the left subtree for node 70 is 3. Height of the left subtree for node 70 is 3. Sir, how? Because students, there are three levels are there. One level of 30, second level of 15 and 40, and third level of 45. So due to three levels, the height of the left subtree is 3. Okay, now what is the height of the right subtree? So height of the right subtree is 2, because 90 at one level, 85, 95 at another level. So balancing factor for node 70 is plus 1. Fine. Now again, the next example number 3. Let's start with 30, 85 and 98. So all three nodes are known as leaf node. Balancing factor is 0. I'm just writing down the leaf node. One balancing factor 0 at 30, then 85 and then 98. Okay, now let's move further. So students, next we have 95. For node 95, here the left subtree height is 0 and the right subtree height is 1. So 0 minus 1 becomes minus 1. So here it is. For 95 we have minus 1. Okay, now for node 90. Okay, so on the node 90, students, the left subtree height is 1 and the right subtree height is 2. So 1 minus 2 becomes minus 1. So on the node 90 we can write minus 1 as our balancing factor. Now next we have for root node 70. Now if you can say that for the root node 70, students, in left subtree we have only one level height. On the right subtree, see how many levels are there? One for the 90, second for the 85 and 95, and third for the 98. So here the right subtree contains three levels. That's why the height of the right subtree becomes 3. Okay, so what is the balancing factor for root node 70? That is 1 minus 1, 2 and 3, which just becomes minus 2. 1 minus 3 becomes minus 2. Okay, so the balancing factor for the node 70 is minus 2. So this tree is violating the rule of AVL tree. That's why it is known as unbalanced write heavy tree. Okay, so that's it for today's lecture. Thank you so much, students.